All right. So extension equals to new length minus original length. And if the question is compression, compression is also represented by x, and compression आपकी होती है original length minus new length. क्योंकि once you compress something तो उसकी original length ज़्यादा होगी and new length would be smaller. So greater length में से smaller one minus करेंगे हमेशा. Another formula that we have, very important one, elastic potential energy. So right now I'm just listing the key formula that could be used. EPE 1 over 2 F times X. Another formula of elastic potential energy is 1 over 2 K times X square. Another formula of EPE, elastic potential energy, is area under Fx graph, force extension graph. Please keep noting down these important points. Elastic potential energy, change in elastic potential energy, delta EPE, that equals to 1 over 2 K x2 square minus x1 square. This is change in elastic potential energy. Next one, we have stress. Stress is represented by this symbol sigma, that equals to force per unit cross section area. Force should be in Newton, area should be in meter square. If it is in some other units, you need to convert it. Then we have strain. Strain is represented by the symbol, this one. That's the name of the symbol, sigma. This is the symbol for extension, which is epsilon. And that equals to extension or compression over original length. And it has no unit because both of them could be in meters or centimeter, would be cancelled out. Then we have Young modulus. So Young modulus equals to stress over strain. Stress equals to force over area, and strain equals to x over L. So x here over L goes upstairs. So Young modulus is represented by the symbol capital E, and that equals to F L naught over A times X. So this is the expression for Young modulus. The gradient of force extension graph in such a way that you have force on y-axis and you have extension on x-axis. It could be extension, could be compression. Then the gradient of this graph would give you spring constant K. But once you're finding the spring constant, make sure you consider these two things: unit conversion and including the exponents. So all the odd units, for example, if the spring constant is asked in Newton per meter, so you need to convert centimeters or millimeters into meters. And usually exponents are also given on the axis. If you find the exponents on the axis is the plural of axis. So if you find the exponents on the axis, you need to consider the exponents also. So this is just the basics that you need. This is the least that you need for this chapter. For deformation, you need to know at least these formula, and plus then we have the combination of springs, series, and then parallel. If the springs are combined in series and parallel, in series the total extension equals to the sum of the individual extensions. For example, we have two springs, then the total extension would be the sum of these. Likewise, the total spring constant in series is found by the reciprocal method. 1 over the total spring constant equals to 1 over k1 plus 1 over k2 plus 1 over k3. If you have two springs, then 1 over k1 plus 1 over k2, or you can use the shortcut product over sum. For parallel springs, once the springs are connected in parallel, so by the way, series springs look something like this. First one, second one, third one. Okay. And the ones parallel will look something like this. 1, 2, 3. These three are connected in parallel and they are holding a load. Let's see. So these are connected in parallel. The total extension in parallel is found by using the reciprocal method. So the formulas are swapped. If you could notice, the formulas are swapped. And the total spring constant equals to k1 plus k2 plus k3.